This is lecture 9F on mixing problems for Calculus 2. You might remember from algebra the kind of mixing problem where you had some 3 milligrams per cc of some solution, say you had 10 cc's of it, and 10 cc's of another concentration, say 10 milligrams per cc on that second concentration. But you needed 6 cc's of a 5 milligram per cc solution. Usually it was presented as a problem for a pharmacy. To solve this problem, you ended up with a couple of equations. You had to decide how many volumes of each, and those had to equal 6. You had to pick so many volumes out of that first concentration, which you had 10 cc's, and so much of a volume, so many cc's out of the second concentration, and come up with 6. But the concentration, you had this, let me get the pen. This equation told you how much of each substance you had. You took the concentration and you multiplied it by volume and found out how many milligrams you had. And you got so many milligrams out of each and ended up with so many milligrams in your final solution. So let's write that in general. Concentration from 1 times the volume in that first tube that you were working with, plus concentration in the second vial or whatever times the volume that you're taking from that one. That would give you, so concentration, let me do it in units. Just talking about it. Okay, you have so many milligrams per cc, and if you multiply by volume, which is in cubic centimeters again, you end up with milligrams. How many milligrams of the substance you have? So this gives you amount. In other words, something in milligrams, how much substance you have, and this other was just the volume. Now in these algebraic solutions, the idea was figure out how much you need of each, mix them together, and get your final concentration. That's the algebraic problem. If you want to study the problem while the mixing is occurring and watch what's happening as you mix these things without having necessarily a final goal on it, then you need to use calculus. So for the calculus problems, we're going to require the concentrations and the volumes, but we're also going to look at the rates at which the concentration and the volumes are changing during this mixing problem. In this typical calculus mixing problem, and the ones we're going to discuss here, we have some kind of a tank or a room, some kind of an enclosed volume, and a substance with one concentration is entering the room, and a substance with another concentration is leaving the room. And the setup is a major part of this problem, so if you can follow that through, you'll find that you can solve the problems fairly easily. So what we have to do is derive these equations, and that, like I say, that's the hardest part of the problem. Then we'll set up 2 types of mixing problems, one with a tank or a room that has a constant volume in it, and another where the volume is changing. We solve these equations using integrating factors. What we solve for in these problems, at least initially, is the amount of the substance. In other words, the milligrams. And we're going to call that variable y. Doesn't look like it's a good choice, but that's what we're going to do. Okay, so what we want to do, what we're going to say here, this is a general idea, is the rate of change of the substance in the tank equals the rate at which it enters the tank minus the rate at which it leaves the tank. For example, in one of the homework problems, we have a car parked at the air intake of a conference room, and the car is spewing carbon monoxide. So we want to look at the carbon monoxide, how much carbon monoxide is in the room. The rate of change of the carbon monoxide in the room is equal to the rate at which it's entering, again it's the rate at which it's entering the room through the air intake, minus the rate at which it leaves the room. So you have some kind of a circulating, cleaning air system. So then you can equate the carbon monoxide that's entering the room and minus the carbon monoxide that's leaving the room, and that will give you the rate of change of the carbon monoxide in the room. If we remember, we had an expression for the amount of a substance, the concentration times the volume. And as I said before, concentration was, for example, in milligrams per cc, and if volume is in cc, those units cancel and you end up with just milligrams. That's what we're talking about. Now, I want to know the rate, so I'm going to take the time rate of change, a derivative with respect to time of that expression, C1V, which is the amount of the substance. No one tells me I have so many pounds of carbon monoxide. They'll say it is per, parts per million. It's going to be a concentration. So I have to multiply that by the volume. When I take this rate of change, we're going to assume that this concentration isn't changing, although in a more complicated problem it might be. So taking the time rate of change of concentration times volume gives me C1, concentration not changing, times dV by dt. This is going to be the building block for deriving these equations. So if we want to know the rate at which a substance enters the tank, that would be the input concentration times the input flow rate. So it's Cn times the input flow rate, which is the change in volume divided by T, the amount that's entering the room. So the Cn in that problem I was talking about would be so many parts per million of carbon monoxide times how fast that air is being sucked in through that air inlet, into the conference room. So here's another example. If the input concentration is 25 milligrams per cc and the input flow rate is 4 cc's per second, then the rate that the substance is entering the tank is, those two multiplied together give me 25 times 4 is 100 milligrams per second. See, that's milligrams, amount per second that's entering the tank. Now let's look at the rate that the substance is leaving the tank. That would be the output concentration times the output flow rate. So it's output concentration times the flow rate. This is the volume that's leaving the tank. Now we're going to make an assumption that it might seem highly unphysical. And we're going to assume that the substance in the tank is immediately and thoroughly mixed. Right? So it's like this. Here's this room, okay, and right over here is some input and some concentration. Here's the flow of the substance into the room, and remember this is in milligrams per cc per second. I'm sorry. It's flowing into the room. Over here, let's put that in green. Here, whatever in the room is getting pulled out, if indeed it is. And so this would be C out times how the output flow rate. Right. Well, physically, you could surely say that if you're sitting over here, right here at this part of the room, you're going to get a higher dose of this input than if you are over here by the outlet, because of diffusion. When it comes in here, it's got to move and get mixed up throughout the room, this C1. But we're going to assume that as soon as it comes in the room, it's immediately mixed by some gigantic ceiling fan or something. Right? This is not a physical assumption. But it might be reasonable in some cases, and we'll go ahead and do the problems this way. If you want to study it in the kind of detail that I've done in this drawing, you have to use numerical methods. And you'll have to set the problem up maybe similar to this anyway, so let's go ahead and set it up. All right, here is the idea. Now with this assumption that everything is equally and thoroughly mixed in the tank, the output concentration equals the tank concentration. Because everything in here is mixed, and so when it's all mixed up, that's exactly what's going out the output. All right. Now, what is the concentration in the tank? You want... Okay, concentration is amount divided by volume. That would be a concentration. If I have, say 3,000 milligrams and 1,000 cc's, the concentration is 3 milligrams per cc. Right? That's a unit of concentration. So it's the amount divided by the volume. But if you remember before, we said we're going to solve for the amount, and the amount we were going to call Y. and the volume of the tank is just the volume of the tank. Could be changing in time, and we'll talk about that in a minute. So the output concentration, here's the output flow rate times the output concentration. Okay, the output concentration is the same as the tank, so I did that. Now I know how to compute that. That is Y, the amount that's in the tank divided by the volume of the tank. Alright, we're almost set up here with this. Okay, so now we're going to say that the rate of change of the substance in the tank equals the input concentration, what's coming into the tank, times input flow rate, minus the amount that's in the tank divided by the volume, that's the tank concentration and also the output concentration, times the output flow rate. Alright, now we've got to say something about the tank. The volume in the tank is like problematic right now. The volume in the tank is the original volume that you started with plus the rate that any kind of volume is coming in times T minus the output, how much volume is leaving the tank times T. It would make more sense maybe if you think of it as a fluid in terms of a liquid, that you could be putting a liquid into the tank and draining it off so that the volume would change. You start with the original volume. Here's my tank. Here's a certain amount of liquid in it. So if I have this one pipe that's as an input here, and there's an output here, this is your output, and this is your input, obviously the volume in the tank is going to change. If they're equal, it won't change. If the amount you put in is the same as the amount you drain out, then the volume will remain constant. But if you put more in than you drain out, then the volume in the tank will be increasing, and vice versa.